So in the last video, we looked at how we could actually use already determined thermochemical equations to calculate the amount of heat that's exchanged for, a certain amount of reactant or an amount of product that's made, what happens to the heat during that process. But a lot of times you'll actually be needing to measure the enthalpy exchange or the heat exchange when you don't actually know what the chemical reaction is, or if you're wanting to actually determine what the heat, the thermochemical value, the delta H or the enthalpy is for a new chemical process. So one of the methods by doing this, to do this, is called a calorimetry. And there are a couple of types. There's actually the bomb calorimetry, which we aren't going to cover in this class. It's a neat thing, but we're going to kind of focus on the major topics, and so we're going to talk about coffee cup calorimetry instead, which is a little bit more accessible to most chemists, and it's used quite a bit. And so the way the coffee cup calorimeter works is you have a chemical reaction that you do inside of a thermally insulated container, e.g. a coffee cup. A lot of times you notice it's like doubled up, is so that way you get double the insulation. And you have the chemical reaction happen in this water, and then you measure the temperature exchange for the water. The reason why we use water is because it has a high heat capacity, a high specific heat, and so because it has a high specific heat and doesn't exchange heat very fast, you can actually just measure the temperature exchange, and very little will be lost to the surroundings, especially if you have it sealed. The better you have it isolated, the better your numbers end up being at the end. So we use that equation that we saw from Monday, where we have the heat of the reaction can be essentially the mass of the solution or mass of the chemical times the specific heat of the chemical times the change in temperature of the chemical. But realize we're not actually measuring the heat exchange or delta H for the reaction directly. We're actually measuring the heat exchange for the solution. So the idea is the heat's going to come off the reactants, but the reactants are in the solution, in the mixture of the solution, and we're measuring the actual heat exchange for the entire solution, not the reactants within it. So the system is the chemicals in the solution, but the surroundings is the solution itself, and so it's exchanged to the surroundings. So we have the delta H of the solution, the heat exchange that we calculate with this is actually the negative value for the heat exchange for the reaction. So we just to kind of define the reaction or the Q for the reaction as just we kind of skip out of this part and just do negative the mass of the solution that we're using times the specific heat of the solution times delta G. And we do use the specific heat for water because these solutions are mostly water, and so the specific heat of the solution is very close to that of water, so it only adds a small amount of error, just making this assumption that those two things are the same. So how does a calculation look like for this? These are very much based on calculations. So it looks like this. So when a student mixes 50 milliliters of 1.5 molar hydrochloric acid and 50 milliliters of 1.0 molar sodium hydroxide in a coffee cup calorimeter, the temperature of the resulting solution increases by this much. Just calculate the enthalpy change for the reaction in kilojoules per mole of HCl, assuming that the calorimeter loses only negligible heat. Total volume of the solution is 100 and density is 1.0 grams, and the specific heat is 4.18 joules per gram Kelvin. Oh, what do we do if we have Kelvin here? Oh, we'll look at that in a second. So looking at this particular chemical reaction, one of the things you have to ask is how many moles of sodium hydroxide were reacted? Because notice that we're going to calculate the value in kilojoules per mole. Oh, how many moles of hydrochloric acid were reacted? Well, if you look at the amount that's given in volume, 0.050 liters, I'm converting it to liters because we have the value in molarity. Actually, let me put a decimal place here and here so we have at least 2 sig figs in our answer. So we're looking at this. Oh, and I'm going to put liters of hydrochloric acid, HCl. We want to see how many liters of sodium hydroxide we actually need to completely react with it, we would do the stoichiometry, use the stoichiometry, and we would say, well, there is 1.0 moles for every 1 liter of HCl. Well, if we look at the balanced chemical equation, it's 1 sodium hydroxide for every 1 hydrochloric acid molecule or moles of molecules. And then we go to the other side and to find out how much volume we need, or how much sodium hydroxide we need, we would actually use the molarity of sodium hydroxide and say 1.0 moles of NaOH for every 1 liter. And when we get to the end, what we would find out is we need 0.050 liters of NaOH. Well, what does that mean? That's the same value that we started with. It means that in this question, in this theoretical question, we're given equal amounts of reactant and product. And so this is not a limiting reagent problem, but if it could have been. It could have been if we didn't have equal concentrations, equal volumes, and a 1-to-1 molar ratio. This definitely could have been a limiting reactant question. So if we go through the calculation, do the 0.010 liters of hydrochloric acid times the 1 mole per liter, we of course have 0.050 moles of HCl that's in there, and it is completely reacted. Remember, we already figured it out. We have exactly equal amounts of sodium hydroxide and hydrochloric acid, and so we are completely reacting all 0.50 moles of HCl. Now going down and using the delta H is equal to negative Q of the solution. So we're going to say Q reaction is equal to negative the mass of the solution. So if we have 100 milliliters and 1.0 grams per milliliter, let me also put a dot here, we would do 100 milliliters times 1.0 grams for every 1 milliliter, ml. And then we end up with, of course, 100 grams with only 2 sig figs in there technically. We got 100 grams, so we would put this down here. Let me put the negative in there. Ooh, actually, let me extend that out just a little bit so the negative's easier to see. Negative in there, and then we got a value. We've got 100 grams times, remember it's MCS delta T, in this case a negative MCS delta T, and times the 4.18 joules per gram degree, then we got gram Kelvin. Wait, I thought it was gram degrees Celsius. Well, the neat thing is the size of the unit for Kelvin is the same as the size of the unit for Celsius. So if we change, remember we're doing delta T, if we have a change in temperature, the value in Kelvin and the value in Celsius will be the same. However, the absolute temperature of the end point or the beginning point will be different. This, by the way, delta T is what's called the state function. Doesn't matter what we're starting with or what we're ending with. It only matters in what the difference between starting and ending is. And so we're looking at these things. And then now we're going to go to this last little bit where we have change in temperature. And then we're going to put in the values, which is 27.5 degrees C minus 21.0 degrees C. And so the difference in our temperature change is 6.5 degrees Celsius. I just did that in my head so we can just do the multiplication and division all together. So we got 100 times 4.18 times 6.5. Of course, this will be a negative value, but we end up with negative 2,717 joules. Notice our units. Oh, here we'll put Kelvin in Kelvin. Excuse me. Our units are Kelvin. Kelvins would cancel. Grams would cancel. We will have units of just joules. And so we take this negative, to change this into kilojoules, 17 joules, just in case you're rusty, right? There's 1,000 joules in 1 kilojoule. Remember, kilo means times 10 to the third. So we have times 10 to the third joules in 1 kilojoule. And then the last step, so it's 2.0 a negative 2.717 kilojoules. That's the total amount of heat that's exchanged, but then we want it to know on a per mole of hydrochloric acid used, and so we would divide this by the moles of hydrochloric acid used. And so at the end, will be divided by 0.5, 2.717 divided by 0.05. And so we end up with a negative 54 kilojoules per mole as our answer. And so this is what's called a copycat calorimetry calculation. You do need to know what is the stoichiometry for the reaction, how much reactant is being used, and that sort of thing. But this allows you to calculate the amount of heat exchanged on a per mole basis, or just the total amount of heat exchange, as is the case, as we did during this process up here. So go ahead and go try out the Chem 101. That'd be chapter 9. The fourth set, or excuse me, chapter 10. Excuse me, the fourth set of questions. And hope to see you tomorrow during the conference, or today for you. Bye.